Okay. Great. So for the next part of this, I hope that you all have R installed or you have a laptop at hand. Do you have a laptop nearby? People do. This is good. Go ahead and grab those out. So for a starter, it might be worthwhile to ask if people know where R got its name. Have you tried searching for anything about R online? That can be really difficult, actually, because R is just one letter, and there are lots of terms that incorporate the letter R. But R got its name from some software that a lot of statisticians use called S and S+. And this commercial software was really good, and a lot of people really loved the power that it afforded them, but they wanted something free that they could use. And so some programmers started the R project. There are actually some analogs for other statistical software as well. Has anyone heard of SPSS? SPSS, a few people have. So there's an open source clone of that called PSTP, just to compound the problem. So Linux people, I think, have established that they're really bad at naming things, but that's okay, that's fine. So I wanted to talk a little bit about types, structures, and of course about the looping and software flow. I'm going to reopen RStudio on here. And I'm going to change so it's just doing a duplicate of my screen. Okay. That's not very visible, is it? I'm going to change resolution. Graphics properties. And I'm going to switch up to 720. Actually, I'll switch to that. That'll be good. Okay. Is everyone able to start RStudio okay? Or R? Or not? We'll just deal with it. It'll be fine. Okay. So we're going to start with data types. If you are a programmer, you probably already have some notion of what data types exist. If I say something like a float to you, or an integer, you probably have some clear notion of what that means. But I appreciate that many of the people in this room have probably never programmed before. And I want this to be accessible to you. So if you're an expert programmer already, I'm going to ask your patience, because this is stuff that everybody needs to be able to understand. There are 6 types of atomic data structures available within R. I can help you with that. All right. So they are called logical, integer, real, complex, character, and raw. Those are pretty fundamental, and you can see that it's spending an awful lot of its time on numeric values, because it is, after all, a statistical package. But I think it's important to talk through those just a moment. We've already seen an example of my using a logical variable. Remember when we ran read.table a while back in the video? I had to specify that this file contained a header. And I said header equals t. That's an example of a logical variable. I set header to true, which meant that the software reading the file knew to interpret that first line differently than as though it were just part of the rest of the file. So we can create variables very easily. You could just say a equals true. Well, I'm just going to do it this way. A equals true. Okay, so now I've created a new variable. It has a type to it. So if I say type of A, I can see that this is a logical variable. It's got a true value or a false value. You can do math with them. You can say B equals false. Okay? Now, I want to point out that my very first time to appear on TV was as one of those kids on a math show on public TV answering logical questions, right? So let's try this. Okay. A or B. Ha! No, I've done this wrong. Hee. All right. Goodness me. Okay. All right, I've done math here. That might not be clear, but this is Boolean math, Boolean logic. So we set A to true and B to false. When I said A, pipe, B, I was asking a logical question. What is the value of A or B? That's confusing, isn't it? A or B. A is true, B is false. What is true or false? It equals true. The reason being that in the OR function, if any of the inputs are true, the output is true. But that next thing I used, A and B, means that both of them must be true if the output is to be true. Okay? Maybe you've encountered some Boolean logic along the way. That's the kind of way that you implement that in R. So these are logical variables. You can do math on logical variables. Okay, I'm going to mention 3 kinds of numerics. Oh yes, a question.
Well, when you type in like a slash, do you have to put the space there? Like between a and the space?
You do not. Yeah, white space doesn't really matter in this case. Think about if you had 2 numbers and you put a plus in between them. Having a space appended to it or inserted in there doesn't really make a difference. The mathematical sense of it is still accurate. Good question. All right. I'd forgotten the syntax on it, so I'm glad that they use the standard convention of or and. Okay. So integer, real, and complex are all numerics. In practice, most people don't use complex numbers a lot for their R code. Does anyone know how a complex number differs from a real number? It would be really funny if someone stuck their hand up and say, I, because complex numbers differ from real numbers by having imaginary parts. Does everyone remember the square root of negative 25? 5 what? 5 what? Square root of negative 25 is 5i, because I is the square root of negative 1. That's called an imaginary number. Most people don't mess with that stuff, so that's fine. So, and then there's string and character. You can store labels, text labels, as part of a variable. We've already seen an example of that. Remember when we had the labels read off of the A versus B file, the labels column was just the letter A or just the letter B. So we can store string or character information in variables as well. And then the last one, raw, is really something that we're not going to worry ourselves about. Now, I used a function here just a moment ago, this type of thing. So let's try a couple examples. I have A is 3 and B is 4. I can run type of on A, and it reports that it's a double. So it's an integer type essentially. Okay, can I do ordinary old math with that? A plus B, 7. Sure. Okay, so all that stuff is working just as you would expect it is. Okay, so these atomic variable types get combined in order to create more complex data structures. So we're going to try to work our way through some examples of that so that everyone can understand it easily. So we're going to start with vectors. Vectors are probably the most widely used type of data structure in the software. So what's the most... Can I make this font size much bigger? Because I think that would help. I've got view, console changes, session changes. Well, I'm just going to do zoom in for now. See how that does. Okay. So I'm going to create a vector using one of the most frequently used functions, the C function. So let's create a vector. We'll call it A again. And this time I'm going to create a whole bunch of values inside C here. All right. Is this monitor blocking views? I'll just hit enter a few times here to roll it up a bit. Okay. So in this case, I've used a function. You can tell it's a function because it's got these parentheses after it. The function c is given the numbers 2.7, 2.7, 3.4, and 1.6. And that function has combined these four values into a vector that is stored in A. So it made a whole lot of sense to everybody when I said A equals 3 or A equals 5, right? This is not fundamentally different, except that we're storing a whole vector of numbers in one variable instead. So if I just type A by itself, I get those same numbers back in list form. So R is really, R forces us to think a little bit differently about numbers because a variable can stand for a whole line of numbers, a vector in this case. All right. Now, one of the functions that's pretty fundamental to understanding these vectors is the length function. So I can ask, what is the length of A? You can see that I fed it four variables, or four numbers, 2.7, 2.7, 3.4, 1.6. And when I run the length on A, it returns, there are four variables within that. All good so far? Good, good. Okay, so the length function is very valuable for that. There's a very important thing that we need to talk about, though, in connection with this, and that is indexing. Indexing means that I want to look at some particular number, some particular member of a vector. All right, so let's use some examples of that. I'm going to start, and indexing is a type of expression that uses square brackets to it. So I'm going to say A square bracket 2. Well, it's kind of ambiguous in this case because the first two values of A were both 2.7, and when I run it on the second element, it returns that value. If I use A3, I'm able to pull out 3.4. It's the third value in a vector of 4 items. All good so far? All right. Now you can do some squirrely things with this as well. So let's start with a new syntax here. I'm going to use 2:3 for the value I want to index out of this. And you can see that the software has retained the second and third values. This 2:3 business means 2 through 3 inclusive. If I were to say 1:3, it would give me the first 3 values of the vector. 1, 2, and 3 are returned by 1:3. So if I say 1:3 all by itself, you get the numbers back. You can make that arbitrarily large too. You can say, give me every number from 15 to 23, and back pops that whole list of numbers. So anytime you want to grab out a whole series of numbers that are consecutive like this, you can use the colon operator to give you back that information. One other thing that you can do, I'm going to set up our vector a little differently this time. I'm going to make it A, B, C, D. Okay, A, B, C, D, easy, right? Now I want to grab out the first, third, and fourth from this vector. So I'm going to say A colon C. I'm going to use my compose function again, and I'm going to specify. Did I say the first, third, and fourth? I said the first, third, and fourth. Okay, so 1, 3:4. You see that? So I have the value 1 followed by 3 followed by 4, where I've said I want everything from 3 to 4 appended to number 1. And you can see that it pulls out the first, third, and fourth item in a long list. To make that a little clearer, I'm going to make a variable called alpha, and I'm going to make it equal to A through Z. Ha! What'd I do? Oh, I need to actually quote that. I'm sorry. I just botched something terribly. Ha! Tell you what, we'll just do this. There we go. Alpha is 1 through 26. So if I wanted to grab out just the subset that consists of the 5th number and the 7th through 9th, wow, I'm really not thriving on this today. Oh, sorry, it's called alpha. Alpha, square bracket, C, 5 comma 7 through 9. There we go. The software is able to recognize that 7 colon 9 means that I want 7, 8, and 9 all together, plus 5, which I threw in there through the compose function. Okay, so subsetting allows us to grab out just a specified part of a vector. Everyone feels good about vectors. We can store multiple values in a variable. The other thing that I must specify about vectors is that they require that they be all the same type. All the same type. So if we look at this, we see that I can create a variable called 2.3, comma 4, comma 8. Oh goodness, what am I doing wrong? Oh, sheesh. I forgot my compose on it. 2, 4, 8. There we go. A is 2, 4, 8. No problem there. What happens if I change one of these to a floating point number, a number with a decimal part? So let's change this so that this is now 4.18. You see what happened? Changing one of these numbers from an integer to a floating point number forced all of them to be treated as floating point numbers. So that's really important. The software is going to use whatever type for that vector can hold all variables that you've given it, or all values that you gave it. So by specifying that one of these numbers was a floating point, all of them were compelled to be floating points. Now let's try something even crazier. Now I'm going to add in the letter Z on top of this. What happened? Now, by including a single letter, all of them were forced to be strings. So I gave it Z as a string to be combined with a bunch of numbers. Those numbers are now treated as strings as well. Okay, so that's a start with vectors. I hope that's a useful place to start. From there, we're going to talk about matrices. So a matrix is awfully useful for a wide variety of types of math operations. So how do we create one of these? Well, we're going to start with the matrix command. So let's say M is our matrix name. What values do I want to... Okay, I've thrown a whole bunch of nonsense in here, so let's first off make sure it runs, and it does. I'm going to hit M and hit enter. Okay, so let's pull that other stuff off screen. Okay, so I have a whole bunch of different pieces to this. I want to walk you through it. I am using a function called matrix to create a matrix. If you just use C by itself, you're going to get back a vector. But in this case, I'm using matrix in order to generate a matrix. I'm specifying that this is going to be 3 rows tall and 3 columns wide. That's what my n row and n col business is. I've also given it a series of numbers, C987654321. I've given it 9 values to put into that matrix, just specifying it through the C command. So essentially, I'm passing it a vector of 9 numbers and telling it, format these as a matrix for me. Everyone getting that? All right. I've also given it a by row command. I'm specifying that the values I'm giving it are given in row order. So it sees 987 should be written in the first row. It knows automatically it's run out of space in this row because I specified the number of columns would be 3. So when it comes to processing the 6, it says, aha, I have to start the next row in order to write those at 654. Again, it's run out of space, and it comes back down to the next row, 321. So, did I need to specify all of that? No, actually I didn't. Because R is clever enough that if you leave out the number of columns, it will still put everything in the right place. Because if you know the number of data points and the number of rows, you already know how many columns there are. A matrix is required to have exactly the same type of data in every cell, and it's required to have every row with the same number of columns in it, and every column with the same number of rows in it. So by giving it the number of rows and the number of data points, it can divide one by the other to find the number of columns. All right, let's mess with its head a little bit. So with matrix, let us now give it one more number. I'm going to give it comma 0 here. All right, what happens? It throws an error at me. The data length 10 is not a submultiple or multiple of the number of rows. So, but R is going to mess with R heads next. Now, I'm going to redo that, but this time I'm only going to give it 3 values, not 10. So, it knows that there are 3 rows. We're also going to specify that there are numbers, that there are going to be 3 columns, and we're giving it 3 values. So we're specifying a 9-value matrix, but only providing 3 rows. Why didn't it throw an error? It didn't throw an error because R says, oh, well, you only gave me the 3 data points, so you must have meant to duplicate them on each row. Sneaky, huh? All right. So be really careful when you're creating these matrices that R isn't messing around with you. It's always a good idea, having created a matrix, to type in the variable name and see what it looks like. Does that look like it's supposed to be? Because your data may not get to where you expect them to be, especially if you're giving something other than the number of elements that that matrix is supposed to contain. All right? Great. So, right. Sometimes you can create matrices by other means as well. So I'm going to create a variable called C1 and dump into it 1 through 3. I'm going to create another called C2, and I'm going to dump in the values 4 through 6, and a third one called C3, and I'm going to dump the values of 7 through 9 in there. From using the series operator, remember, it's going to give me every value including those. So 1, 2, and 3 is the response to 1:3. Okay, so I have these 3. Right now, they are three vectors, but what I want to create is a matrix from them. So for this, I'm going to create another, I'll call it row matrix, is equal to rbind C1, C2, C3. So I'm using the rbind function, the row bind function, to create row M. And then I'm going to do this a second time, going in the other direction. cbind, C1, C2, C3. Okay, so how are these going to differ? They're going to differ because in the one case, the variables given to be bound together are treated as rows, and in the other case, they're treated as columns. So when I look at row M and row C, even though they're built from the same data, they've got the variables in different places, right? So C1 contained the numbers 1 through 3. We can see that in the row bind case, that whole variable was treated as a row. But when I look at the cbind case, they're all treated as one column. So matrices can mess with you a little bit. It's worthwhile to take a look at the output once you've created one. Okay. Indexing. We talked about indexing with vectors, which was pretty straightforward. You just say essentially which numbers do you want out of it. Matrices can be a little tricky though. So I'm going to use row M as our example. I want to grab out the third row of this matrix. So I'm going to specify 3 comma nothing. And as you can see, I've got 2 spaces for numbers here. In any matrix, you're going to have to give 2 dimensions. I gave it row 3 as its first dimension, to say the 3rd row of the table, but I didn't say anything at all about columns. And by default, the software returns all of the columns. So if I say row m 3 comma nothing, it's going to grab out all 3 of those values. I can also use indexing to grab out a column. So if I were to use row m nothing comma 2, I will grab out 2, 5, and 8. It's grabbing out the 2nd column instead, all of the values in it. So this stuff shows up all the time. As the students from our division move into the biostatistics module, a lot of these things are going to be expected of you to notice as you move along. So it's really worth it to you if you're able to make a few examples of this sort yourself and see if it makes sense to you. So creating matrices enables you to take on certain functions, 2D histograms for example, but you need to be sure that the data are getting where they are intended in that matrix. Okay, there's the example of lists. Lists, we've already seen an example of that. Remember, we did a histogram a while back. So if I have a variable, I'm going to use a very friendly function here. You see rnorm? In this case, I'm taking random samples from a normal distribution. So I've told it, give me 1,000 random numbers coming from a bell-shaped distribution. So I can confirm that looks right by doing a quick density plot for it. There you go. I sampled 100 numbers from a normal distribution. When I plot them, they look sort of like a normal distribution. Oh, sorry. I'll move that up a little higher so you can see it. I didn't realize my screen was going to be in the way here. So in this case, we were able to create a vector of 1,000 values from the normal distribution just using the rnorm function. It's one of those examples of things that would be really hard to do in a lot of math environments, but here it's just a one-liner. So from this vector, we want to create a histogram object. So I'm going to create a histogram object, and I'm going to store it in H. And when I type H by itself, I get back all of this information. So you should remember seeing something like this, because when we did the video on R to do the frequency breakdown to do the histogram, we got back an object like this. So I've done the same here. You can see that H is a list. H starts with a section called breaks. It continues with a section called counts. It continues with a section called density, has midpoints, x names, equidistance, etc. We have all these different fields that are in one object. So this is not a matrix, obviously, because a matrix requires you would have to have the same number of elements in each row and in each column. That is not true of a list. In this case, breaks is a series of integers. Oh, sorry, a series of floating point numbers, rather. Counts is a series of integers. Density is a series of floating point values, mids, and so on. And then when you get down to here, you have variables that have only one element in a list, and they're text, they're character strings. So lists have this amazing non-uniformity about them, that you can store any number of things in a long laundry list. And you have no requirement that those lists be the same in length, although many of these are. Okay. Now I'm going to give another example, and that is the data frame. So if I were to use the read table, for example, I get back a data frame that is like a list. But data frames are special lists. Here we saw that in the histogram output, we have a list, but the fields are not of the same length. In a data frame, every element of the list has the same length. So if I were to change to a different working directory first off. File, where's my working directory? Anyway, we'll just go to files here. All right, files, histogram box plot. Now we're going to specify this as our working directory. Okay, and when I do my list files function, I can see what files are there. I see my A versus B file is there. So I'm going to reread AVB into a variable. Read table 20180219 A versus B text. And don't let me forget it. What do I need to add? I need to specify header is true. Okay, so in order to read that file, I used a function, read table, that took as a parameter the file name. It took another parameter here called header. I specified that header was the variable I wanted to name and set it to true. The result was an object called AVB. Now, what kind of object is it? I'm going to just run a summary of it first. So remember, summary is always handy to just figure out what the heck did I just create. So I created AVB. It is a data frame with a field called intensities that is numeric. You can tell it's numeric because it's got mean, median, mode, and all that stuff. Not mode, actually. And it also has another variable called labels. And labels has 40 values that are A and 40 values that are B. Labels is a very, very special kind of data structure. It's one called a factor. So the software recognizes that there were only two distinct strings appearing in that column. It read A or it read B. And it counted how many times each of those occurred. So it recognizes that this column of the file should be represented as a factor, something that separates the data set into different types, into the A set and the B set. Okay. One of the most common examples that we would use for a factor is sex, for example, in a table from a survey. You had males and females taking part in a survey that gets coded in some way, but it's no good if some of them read men and some of them read males and others read women and others read females. You want it to be stored in such a way that only different sexes are listed separately. So in this case, labels is kind of a proxy for that. It's a factor. But the AVB itself is actually a data frame. So we have, let me see. We have a couple ways to probe this structure. If I say type of AVB, you can see that it's simply called a list, right? But we have other options for this as well. One is class AVB. You can see that if you look at it a little more closely, this list is actually, it meets all the requirements of being a data frame, which means that every list, every vector within that table has the same number of entries. That's really important. So when we read this file, every row contributed an intensity and a label. As a result, the intensities column of this data frame has exactly the same length as the labels column. Everyone getting that? That is a requirement to be a data frame. It is not a requirement for all lists, but data frames are special kinds of lists where each vector is the same length. So if I were to say length AVB intensities, I get back 80. If I say length AVB labels, I get 80. So I've used something specific to lists here. I used the $sign. Oh, I should scoot that up a little higher. I'm going to keep fighting with that. All right, there we go. So we see that the intensities column of AVB is 80, and the length of the labels column within AVB is 80. using the dollar sign is a quick way to jump to a particular vector within a list. We could have done that with the histogram one as well. If you remember, we had our histogram just a few moments ago that we produced from this Gaussian, from this normal curve. And we had things like breaks, counts, density. Each of those is started with a dollar sign as a reminder to us that we can treat this as an independent list. So if I say h:breaks, I can grab out just that list by itself, or just that vector rather by itself. Okay, so we have seen now vectors, just a one-dimensional list of things. We have matrices where we had a fixed number of rows and columns and all of those data points were filled in. We had lists where we had a compound of different types that were all put together in one object. And a data frame, a list of a special type that has every vector within the list has the same length. Okay, so that took us through a lot with data structures, but I hope that that gives you at least a quick intro to it. I have one other thing I want to talk about, and I've given myself 15 minutes to do it, but I think it's worth doing just the same. We've talked a little bit about Boolean logic. You remember we took a look at A and B and A or B, stuff like that. That's the first part of what we want to talk about next, and that is conditionals. Conditionals. So in a conditional, we are using, we're using a condition like this. And we have two alternative things to do. Let me see if I've got my syntax right. I think I do. All right. Let me see if I've got this working correctly. Oh, it is. How nice. Sometimes I do this in so many different languages that I get my head screwed up sometimes about how to implement these. So let us look now at our logic here. We have a condition here. 3 = 5. That's kind of odd, isn't it? 3 = 5. Why did I do that? Remember that in R, it is okay to say A = 8, for example, with a single equal sign. But that is not a conditional. That is an assignment. If you use a single equal sign, like A = 8, you are setting the value of A to 8. And the result of that is true in most languages. I don't know if it is here. If you use equals, on the other hand, you're asking a question. Are these two things equal? So if 3 = 5 is asking if these two numbers are the same. They clearly are not. If they were, we would print the value true. If they were not, we would print the value false. All right, and when we fixed the math, when we said if 5 = 5, that's self-evidently true, then we can print true, and true is the result. Now, are you required to simply output a false or a true? No, you can do whatever you want from these values. I'm going to show you also some of the other operators that we have available to us. So I'm going to scoot that one up the screen. So far, we've used pipe, the two pipes side by side. That means or. We've used and. That means the logical and. Both things must be true for the output to be true. We've used equals, which means they have to be the same value, or it's false. In this case, I'm using not equals. Bang equals is the same thing as saying not equal to. So if 3 is not equal to 5, print true. It doesn't even need to know what comes after the else because 3 is not equal to 5. So it already knows it's got to execute the first of these. Are you required to give an else outcome? You are not. So if I repeat the same thing without the else here, it still works just fine. Oh. So to explain that, in this top case, I asked if 3 is not equal to 5, print true, and it did say true. But if 3 is equal to 5, which we know it's not, it should print true, but only in the case where it's true. There's no flow, there's no instruction for it if this is not equal. So no result comes from it. So when you're writing software and you have to make a decision about whether you're going to output or not based on some mathematical equation, you can do so pretty straightforwardly. That's an if, well, some people call this an if-then-else because of the old basic structure for typing them. But if-else shows up all over the place. There's barely a programming language out there that lacks an if function. So that's a very helpful one to know. Okay, from there, we can talk about for looping. For looping. Okay, so frequently we have a certain set of numbers that we need to rotate through, and for each different value of that number, we need to do something. So maybe you are trying to remember the powers of 2. This is something that I try to do, especially when I'm trying to go to sleep. If if 11 o'clock rolls around and I'm not asleep, I'm like, okay, 2, 4, 8, 16, 32, 64. How high can you go before you fall asleep? Not very high. All right, so for is our best friend for that. So a for loop is designed to help us to allow an index variable to jump through some number of values. So in this case, I'm going to specify that I is going to start with a value of 1, then rise to 2, then rise to 3, then rise to 4. And while it's doing this, I want to do some math. So I'm going to have it print, I'm going to have it print I squared. Ha! I botched something. Oh! No, what'd I do? Oh, sorry. There it is. There we go. All right. Well, I didn't do powers of 2. I changed my mind about what I was doing. Sorry, let me fix that. I want 2 raised to I. Everyone get that? 2, 4, 8, 12, 16, 32. All right, that's better. Sorry. Okay. So in this function, I is going to take on 20 different values. It's going to start at 1, continue to 2, continue to 3, continue to 4, and keep going up until it hits 20. And for each of those, we're going to print the value of 2 raised to the I power. Everyone have that? So every time we're going to multiply 2 and a bit more. So the hat here represents x raised to the y. Whatever is to the left is the base, anything to the right is the power to which it's being raised. So we see that 2, 4, 8, 16, 32, 64, 128, etc. all the way up until we find our hard drive size. Okay, so that's a for loop. We use them all the time. In good programming practice, you should use a for loop when you know how many times it's going to execute. All right? You don't always know, though, how many times you want it to execute. And for stuff like that, while is a better option for you. So let me say A is now, was there a question on that one? Okay, this time I'm going to set A to 100. So while A is greater than 0, do this. Print A. A equals A divided by 2. Well, it's not quite what I expected. Oh, that's a silly thing. I did a bad function there. Tell you what, I'll change this to something like this. Ha! Oh, sorry, I have to set the value of A back up. A is 100. There we go. So in this case, I wasn't sure how many loops around it was going to go. It's obvious from the code, but let's say I didn't know. And I can say while A is greater than 0, keep doing this. So the function itself looked like this. So I have my conditional right here. Keep doing this until A is until A is no longer greater than 0. Sorry, I realize this blocks it. If I run it, it's going to fail. I think I can hold down Shift there, though. Here we go. There we go. That's my little program. So I started A at 100. While A is greater than 0, print a copy of it, subtract 2 from it. Okay? So that's a simple example of a while loop. Some languages will also have things like repeat until, which keeps operating until a condition is met. It's kind of the opposite of a while loop, but generally the things you can do with a while are feasible by the other method as well. Okay. So with that, you've had a quick comparison, not so quick, of 3 different tools we can use for statistics, all used for the same purposes, histograms and box plots. You've had a quick introduction to the different types of variables that are available to you, the different atomic types within R. You've looked at vectors, matrices, lists and data frames, and even a quick look at factors, which are a pretty important element as well. And you've spent a little bit of time looking at program control, looking at conditional statements, and looking at looping. That's a start to R. If you received the Word document that had learning objectives on it, it spelled out some of the things that I would expect people to take from this. I know I'm supposed to write a test paper question or two about this. So that'll be involved for the students from upstairs. And then our group has a test on this that's built into the bioinformatics module later on. So I hope this is a useful introduction. As you come back tomorrow, we're going to look at some more complex examples of software, especially making use of programming libraries within R. We're going to look at ggplot2. So I hope this was useful. Certainly, I hope that tomorrow we get the projector situation worked out. But that in a nutshell is what we're up to. You guys have the folks upstairs have a test coming up right away. This is not on the test Friday. It's the one after Friday. The one after Friday. You're still safe. Don't worry about it. But yes, data structures, different atomic types of variables, how we code loops and how we code conditionals. These are parts of every programming language. R is a very fully fledged programming language, so there are lots of highly complex things you can do with it. I hope that this gives you an easier, a gentler start as we move into more and more complex examples of it. All right, thank you very much. I will see you again tomorrow, 9 a.m. in this room, and we'll start looking at some real examples of R code. Thank you.